Okay. We'll go from current slide. And we'll pick up from here, but before we get started, let me go over just a couple of things. Number one, I think it's next Tuesday. We have what is called a planning hearing that I'm required to be at. And it's, I think, scheduled for next Tuesday at 10 o'clock in the morning. It won't affect this class at all because we're Monday, Wednesday. But it does affect my office hours, so I want to let you know in case you were happen to be looking for me that Tuesday morning. I'll be on the Birmingham campus. Normally my office hours on Tuesday, Thursday are 10 to 12 and 3:30 to 5:15. Well, the 10 to 12 is almost going to be shot whenever that planning hearing is, which I think is Tuesday, because I haven't figured out whether I need to go straight to campus and get set up and ready for it, or if I can get everything done over the weekend so I can come and teach maybe for an hour and then drive over there, maybe a little more than an hour, drive over there and be in time for the planning hearing. We'll see. So, Tuesday. But other than that, I think my office hours will be fairly set for the rest of the term. Now, what is the rest of the term? I had a couple of students check today, and several said the last day of class is the 31st, which means a Monday. So we'll have class today, next week Monday and Wednesday, and then the following Monday. And then I'll give you your final exam at the end of that class, and you get it back to me either Tuesday, Wednesday, or Thursday. Because I think I have to have grades in by Monday at noon, so I can't be accepting any. Now, technically, we're still supposed to work. We're supposed to work that Friday because we're into August, and Friday is only a 4-day work week, June and July. Except I have an infusion scheduled for that Friday, the 4th, so I won't be on campus at all. My infusion scheduled to start at 8. I have to be there for labs at 7, meaning I'm on, and it usually takes pretty close to all day long. The earliest I've gotten out has been about 3:30 in the afternoon, and by that time I drive out here and do nothing else. So, I probably won't be on campus at all Friday, so I have to have them in Monday, Tuesday, or Wednesday. Tuesday, Wednesday, or Thursday. Okay, and also, while I'm on that subject, this class has been not one of the better ones at getting the research papers in. Only one out of the, I think it's 8 students, 1, 2, 3, 4, 5, 6, 7, 8, yeah. 1 out of 8 students has turned in the paper, so please get those in. This is your next to the last weekend. I'd rather not they all come in on that last Monday, because there's just too much to do. But I'll accept them, but you still get a bonus point if you get them in next week. You don't if you get to do the following week. That's what the bonus point is. Okay. And that last Monday, the 31st, I'll return all tests that I haven't returned so far and all labs that I haven't returned so far. And so far, I haven't returned any labs because one student hasn't turned in any labs. And she's the one that had a pretty bad medical emergency in the first part of the term. I thought she was not going to continue because she hadn't paid either. But then she paid and said she wanted to catch up because she's over that pretty much. And she's been trying. She got 4 tests in, but no labs. So hopefully this week.
Tell me if I received anything?
I think we. Okay, I don't have your paper.
Yeah.
Okay, I got your first lab, first test, second lab, second test, third lab, third test, fourth lab, fourth test, fifth lab, fifth test, sixth lab, sixth test. And I guess today's going to be the 7th lab. So yeah, so you're all set.
So we're going to get, today we'll get a test.
A lab and a test, right?
And then we'll get a test next week?
Or
will
yeah,
it just be
or that may be the final. Well, it depends. We're going to continual relativity today. We just barely got started last time, and we'll continue with this today. It's a fairly long chapter, if I'm not mistaken.
Last summer, like the last chapter we did, that was our final.
Yeah, and that's how it's going to be this time, but I just don't know whether this will be the last chapter or not. It is a long, and it's a pretty involved chapter 2, but we got today and 3 more classes, so I have a feeling we can finish this one. There may not be a lab for this one. I cannot think of very much we can do with this for a lab, so we may not have a lab for this one. Then we'll go back and pick up that where we left off. We did magnetism was the last chapter we did, and the next chapter after that was induced voltages and inductance, which is a really good and pretty easy chapter, I think. And if we don't finish it, then the last test will just cover that. Okay. So I'm thinking that's probably what we'll get done. But we'll see. So, any other questions? All right, where we left off last time was on page 839. This is topic 26, relativity, and we did 26.1, Galilean relativity, named after Galileo, though it's largely connected with Newton as well. And in 26.2, we're talking about the speed of light. Okay. In the 19th century, that's the 1800s, of course, physicists thought that that electromagnetic waves also required a medium to propagate. They proposed that such a medium existed and gave it the name luminiferous ether. Okay? 19th century physicists compared electromagnetic waves to mechanical waves, going up and down on a hose, and seeing the wave travel. And mechanical waves need a medium to support the disturbance, so they thought electromagnetic waves needed a medium. So they made up this thing, the luminiferous ether was proposed as the medium required and had to be present for light waves to propagate. They claimed it was present everywhere, even in empty space where there was no particulate matter. They said it was a massless but rigid medium. I can't get my head around that, how they could have this, but it could have no effect on the motion of the planets or other objects, but it was there as a rigid medium to support light wave travel. Boy, how weird. Okay. I'm almost surprised they dedicated even a slide to that. Okay. Not just one slide, a second slide. Associated with an ether, which basically is some material out there, was the absolute frame where the laws of electricity and magnetism, I'm surprised to write it that way, take on their simplest form. Okay? Now, since the Earth moves through an ether, there should be an ether wind blowing. This is getting weirder. If v is the speed of the ether relative to the Earth, the speed of light should have a maximum A or a minimum B value depending on the orientation of that ether wind. Okay? And this gets even weirder. Okay? So if light was traveling at speed c and the ether wind was following up with v, then the maximum should be c plus v, whatever that maximum speed of the ether wind was. However, if it was opposing, then by Newtonian mechanics, Galilean mechanics, this, which didn't include the speed of light, by the way, this should be C minus V, which is when light was trying to go against the ether wind. All right, we know neither one of those are true, okay? And we know there is no ether wind. There is no luminiferous ether. But how did they claim to verify it was there? The wind could have an intermediate value in between that max and min. The velocity of the ether should equal the orbital velocity of the Earth. So if we were going through that ether, then it was going along with us, and that's why it didn't interfere with us, okay? The change in speed should be detected in the upwind and downwind directions, and supposedly you would see changes in the speed of light. Speed of light, they claim, for the downwind, strange to say that, ether wind, direction would be the square root of c squared minus v squared, where this was in this case, where this was the shorter, this is the longer side, that's the perpendicular angle, and this was the speed of light, which is reduced by that amount, this should be the magnitude of that when you're going against it. Okay? Why are they dedicating this much to it? Okay. Maybe just to set this up. The most famous experiment designed to detect these small changes in the speed of light was first performed in 1881 by Michelson. And do they give a better name? Albert A. Michelson, and later repeated under various conditions by both Michelson and Edward W. Morley. Morley was actually older than Michelson, but not too much. They were pretty much contemporaries. This was designed to detect the small changes in the speed of light, and they were trying to determine the velocity of the Earth relative to the ether. Okay? So this was going to answer both of those questions for them. They were so certain that ether existed, they thought they could do this. Okay? So this was the Michelson-Morley experiment. Okay? Here's what they did. They used what they called a Michelson interferometer. Now what that means is an interference meter, measuring the interference. Okay? So what you have here is a light source. Okay? It hits on this first mirror. Okay? And reflects off this mirror and goes up to mirror 1. Okay? Then comes back off mirror 1, and some of it is so you can pick it up with a telescope here and see that. Okay? Then any that misses the first mirror goes on to the second. This is arm 2, and some goes through, reflects back. What? Pretty lousy diagram, I think. Arm 2 is aligned along the direction of the Earth's motion through space, and the interference pattern was observed while the interferometer was rotated through 90 degrees. The effect should have been to show small but measurable shifts in the fringe pattern of the light that you would see. See, look, some light was transmitted, some was reflected. Some was transmitted, some was reflected. So, yeah. All this is happening, and that made us all the way here in the direction against that ether wind. You should have been able to pick up some changes there. This was their experiment. They set it up this way to measure those fringe differences. Measurements failed to show any change in the fringe pattern. No fringe shift of the magnitude required required by that ether wind was ever observed. Light is now understood to be an electromagnetic wave which requires no medium for its propagation. In fact, it travels best when there is no medium. Okay? When it's traveling through our atmosphere, it does get reflected, it gets messed with. Okay? The wavelength increases. I mean, lots of things happen to it. In void space, it travels best. So the idea of the ether was discarded. So this is one of the few examples that I can think of when the failure, the complete failure of an experiment turned out to be very, very good, okay? Because everyone was convinced it had to exist. This showed it did not exist, and not only didn't it exist, there was no evidence for it whatsoever, and they were wacko for thinking there ever was. But everything that they knew at the time convinced them it had to be there, and they could not discover it at all. Thank you very much.
Have they tried now?
Huh?
Like back then, this is 1800s, right?
Yeah.
So, like, technology has also, like, increased. So I wonder if anyone's ever tried to rediscover it now with all the technology that we have.
To do what?
I wonder
Repeat
if
it?
somebody has tried to, like, detect it now.
Yeah. Well, it so thoroughly got shown that it wasn't even there. There is no substance there.
Yeah.
So they can't. Brianna's here. All right, doubled the class size. Way to go. All right. Just finished talking about the Michelson-Morley experiment, okay, which failed miserably, which is one of the good things that happened, because then that opened them up to consider other things such as quantum theory and things like this. So it's a big part of modern physics that did fail. Okay. So I think we hit all that. All right. Megan is here too. All right. Just finished talking about the Michelson-Morley results. It was one experiment that failed completely and disproved what they were trying to show. Then along came this little guy. Michelson and Morley lived into the 1920s, 1930s. And 1905, this little known character who lived 1879, which was about midlife for the other two guys, to 1955. So what's that, about 21, 76 years old. Okay. In 1905, he published 4 papers. Now, I'm sure people knew about him or little bits about him, or in the field he may have been known. But these 4 papers in 1 year were earth-shattering papers, groundbreaking papers, or at least 2 of them. The 2 on special relativity absolutely changed everything. Of course, we're talking about Albert Einstein. 1916, he published about general relativity, which you would have thought would have come before special, but no, he did special first and then general relativity. And for most of the rest of his life, he was searching for a unified theory that tied all of physics together. He never found it. That doesn't say it doesn't exist, but probably not in the form that he was hoping it did. Many others have continued to do this. I believe, the guy in England who has ALS, Hawkins. I think Hawkins has continued to try to find the unified theory. and probably not just him, many others. Brilliant, brilliant minds, and yet hasn't been found yet. Now, whether there is one or not, can't say. But part of physicists, especially Albert Einstein, really proposed this and followed it. They really feel like physics can't get too complicated. They feel like nature, actually Einstein says, let's see, God is clever, but he's not malicious. You know, those kind of attitudes, that everything really needs to have a fairly simple explanation. It's just that we can't see that explanation, and we make it complicated trying to tie everything up. If you think about the motion of the heavenly bodies around the earth, because everybody knew the earth was the center of the universe, right? The sun rose in the east, set in the west. The stars rise in the east, set in the west. Everything seems to follow that pattern. The moon rises in the east, sets in the west. So everything goes around the earth. Except those pesky little planets, they mostly do, but every now and then they turn around and go in a different direction, and we couldn't figure out why. Okay? Well, generations of scientists tried to perfect the motion of these celestial bodies. One of the big ones was a guy named Ptolemy, who really came up with some clever explanations and suggestions, but every one of them ultimately failed. Why? Because the assumptions were wrong. We weren't the center of the universe. We weren't even the center of our solar system. The sun was the center of our solar system, and we revolved around it. And moons revolved around the planets. And we all went in elliptical orbits rather than circular orbits. And all sorts of things came. Well, Einstein was hoping that kind of a epiphany would break and that he would be part of it, because people found out electromagnetic radiation does this, gravity does this, different things do this, one thing or another. But how in the world do you tie everything together? Shakina is here. And they're convinced, they were convinced, Einstein was, there has to be a unified theory that does bring all these different fields into a fairly simple, it may be somewhat complicated, but into some sort of a construct that makes sense. No one found it yet. Okay? So, let's look at what he did find about relativity. Here are the postulates about relativity. The principle of relativity is that all the laws of physics are the same in all inertial frames. Now again, you might need to go back and remind yourself what an inertial frame is. That's a frame of reference that is not accelerating. Okay? And if you're in a non-accelerating reference frame, then all the laws of physics are the same. If you're in an accelerating reference frame, then nothing seems to fit very well. Okay? Second big point in Einstein's was that the constancy of the speed of light. The very thing that Michelson-Morley was trying to show and measure and identify was totally wrong. So the converse of that was this constant that light does not change speed. Okay. Let me rephrase that. In a vacuum. Okay? Certainly when light goes through a material of different indices of refraction, it does change speed. But the speed of light in a vacuum has the same value in all inertial reference frames, regardless of the velocity of the observer or the velocity of the source emitting the light. Now again, they've got to be an inertial reference frame, not accelerating reference frame, but they can have velocities. So if you are going toward a light source at a fairly high rate of speed, the speed of light never changes. Okay? If you're going away from a light source at a fairly high rate of speed, the light source never changes. Okay? The light speed never changes. That's the constancy of the speed of light. Okay? I think I got one of those flying objects. Okay. I think there may be more than one, but I've got one of them, I think. Okay. The principle of relativity, and then again, this is mostly Einstein, there is a sweeping generalization of the principle of Galilean relativity, which refers only to the laws of mechanics. Okay? The principle of relativity. This is a sweeping generalization of the principle of Galilean relativity, which refers only to the laws of mechanics. The results of any kind of experiment performed in a laboratory at rest must be the same as when performed in a laboratory moving at a constant speed past that first one. Okay? All right, I'll get this again. Results of any kind of experiment performed in a laboratory at rest, you're sitting perfectly still, the laboratory is, you're doing experiments there, they have to be the same as when performed in a laboratory moving at a constant speed past the first one. So if you were in a rail car moving at a constant speed past, your experiment should be the same as mine. Okay? The results should be the same. No preferred inertial reference frame exists. Again, an inertial reference frame is one that you're at a constant speed, not accelerating, inertial. Okay. It is impossible to detect absolute motion. Okay. What do we mean by absolute motion? Let's go back again. Well, I can't find it now. Ah, there it is. That luminiferous effect that didn't exist, but they thought it was, a luminiferous ether, was associated with that ether was an absolute frame where the laws of electricity and magnetism take on their simplest form. Okay? Basically, the relativity, principle of relativity says, on the other hand, it is impossible to detect absolute motion. Okay? Now, they might need a little more definition of that. I feel like they do. But before we go there, well, let's see. Nope, they don't give anything else there too, sorry. And by the way, if you do choose to write on Einstein, I don't remember if anyone's chosen that topic or not, the blurb in your book cannot be your source. You've got to get a source outside the text, okay? Okay, before we get to quick quiz 1, let's do this. The constancy of the speed of light. Okay. This has been confirmed experimentally in many ways. A direct demonstration involves measuring the speed of photons emitted by particles traveling near the speed of light. Okay? Measuring the speed of photons emitted by particles. The particles is traveling near the speed of light. I was going to say, photons travel at the speed of light. Okay, I misread that. Emitted by particles traveling near the speed of light. It confers the speed of light to 5 significant figures. Now, if you had particles traveling near the speed of light, and there was any change to the speed of light, and this was, Courtney, you were asking, have we done anything more? They did. Now that technology has improved and stuff like this, they have now been able to measure how particles traveling very near the speed of light, much nearer than Michelson and Morley ever could have dreamed of, and they still cannot detect any change in the speed of light, even though the light is being emitted by photons that are traveling near the speed of light. Light still travels at the same speed. Okay? This confirms the speed of light to 5 significant figures. It explains the null results of Michelson-Morley experiment that no matter what they did, they could not come up with any fringe benefit, you might say. The motion of the Earth does not affect the fringe pattern, and the null results should be expected, and indeed did happen. The experiment that failed and showed us something, big time. Many experiments in the failure will show us things, but this one was really major. The relative motion is unimportant when measuring the speed of light. Relatively does not affect the speed of light. We must alter our common sense notion of space and time. All right, this is very Einsteinian, okay? He came up with this concept of the space-time continuum, okay? All right, before we hit consequences of special relativity, there is a quick quiz at the bottom of page 841. A true-false. And Courtney heard there's a quick quiz. She's getting out of Dodge fast. No, I'm just kidding. Okay. If you were traveling in a spaceship at the speed of half the speed of light, we don't have any spaceships that will go that fast, but if you were traveling in a spaceship at half the speed of light relative to the Earth, and you fired a laser beam in the direction of the spaceship's motion, the light from the laser would travel at a speed of 3/2 the speed of light relative to Earth. True or false? Yeah, speed of light, you can never exceed the speed of light no matter what. Now, if that's not false, I don't understand this stuff at all. Okay, so let's go back and see. This is 26.1. Okay. 26.1, false. The speed of light is c for all observers no matter where you are. Okay? Even if the spaceship was traveling half the speed of light, fired a laser directly ahead of it, it's not increasing or decreasing the speed of light, no matter where you're looking from. If you're on Earth, that's an inertial system, you know, because it's not accelerating. Okay. So, what are some consequences of special relativity? All right. We're going to restrict the discussion now to only 3 things: length, time, and simultaneity. Okay? In other words, things happening at the same time. Now, this is special relativity. In relativistic mechanics, there is no such thing as an absolute length. What? In regular mechanics, yes. We have our standards. When you're in an inertial reference frame and everything's hunky-dory, there is an absolute length. There is something that is for sure. Okay? But not only that, there's no such thing as absolute time. We'll talk about that a little bit later. Time here and now is different from time if you're in a different relativistic state. Okay? Events at different locations that are observed to occur simultaneously in one frame are not necessarily observed to be simultaneous in another frame moving uniformly past the first one. So it's still a uniform, inertial reference frame, but it won't be the same. Okay? Now again, let me say this. We're talking about things that are traveling very fast, and they're very small things. So when you say they're very fast, that means it's traveling a great distance in a very short time, right? But guess what? When you're doing that, you can't have an absolute length, you can't have an absolute time. How do you know what's traveling when? Because if nothing is absolute. And they aren't necessarily simultaneous. If you were traveling past me at an incredibly high rate of speed, but a constant rate of speed, inertial reference frame, and things that I was seeing that seemed to be simultaneous to you would not necessarily be happening at the same time. Bizarre, but seemingly true. So we'll take that first one, the last one first. Simultaneity. Okay, what do we mean by that? In special relativity, Einstein abandoned the assumption of simultaneity. I mean, did anyone ever assume it? Well, everybody just assumed it was there. I mean, because there was no reason to assume otherwise. He, though, abandoned that assumption that no one would have ever dreamed was even an assumption. They just thought it was truth. Now, he did a lot of thought experiments, and boy, his level of thought was way beyond what mine is, okay? So, here's what his thought experiment was. A boxcar is moving with a uniform velocity. 2 lightning bolts strike at the ends of the boxcar, okay? Strange experiment here. 2 lightning bolts strike at the ends. The lightning bolt leaves marks A prime and B prime on the car and A and B on the ground, okay? So get this, the boxcar is moving at a certain speed. Let's say that table is the boxcar. The boxcar is coming to me at a constant speed. Lightning hits this end and that end at the same time, okay? Strikes the ends, and it hits both this end of the table and the ground at this end of the table. Well, it's a big lightning strike. Hits the other end of the table and the ground at the other end at exactly the same time, okay, on the ground. 2 observers are present. One, observer prime, is in the boxcar as it's moving toward me, and observer O is on the ground over there watching the whole thing, okay? Weird experiment, huh? All done by thought, because I don't think you could ever manufacture this. So that's what the assumptions are. So what is happening? This is a thought experiment setup. This is all a setup here. The observer O is midway, that's the one on the ground, midway between the points of the lightning strikes on the boxcar A prime and A. Okay, that's where observer O is, right when, she's the observer O, he's the observer O prime. This is the boxcar A prime and B prime, and the ground is A and B. And the lightning strikes both places at the same time, okay? The car is moving with the velocity in that direction. And she happens to be right there when it strikes, okay? Now, the light signals reach O at the same time, okay? Those light signals reach O at the same time because she's right there in between, right? They get to her right at the same moment. No matter how long the boxcar is, it get to it at the same moment, okay? He concludes the light has traveled the same speed over equal distances. Okay? That is the guy that's O prime. I assume that's the he they're talking about. Okay? Observer O concludes that the lightning bolts occurred simultaneously. So he concludes the light traveled at the same speed over equal time distances. Okay, good assumption. Observer O concludes the lightning bolts occurred simultaneously. So She thought they occurred at the same moment. Now that E keeps on moving. To observer O prime, the bolt strikes the front of the car first, followed by a second bolt striking the rear. Now, why? I don't necessarily see why he would think that. They hit at exactly the same time. Why would he think they did otherwise? I'm not following that. Okay. I think this is what they're saying. She, looking at this, sees them hit at the same simultaneously. But because he's moving into bolt 1 and kind of away from bolt 2, bolt B prime, and away from A prime, he thinks B prime hits first. Now, that's my best guess on it. I'm not sure I buy that, but we'll take their word for it, that's what he thinks or assumes. Okay? So, to observer O, the two bolts strike simultaneously. To observer O prime, they strike front first, followed by the second bolt striking the rear. I'm not certain I buy that, but it'll be okay. By the time the light has reached observer O prime has moved from where he was. The light from B prime has already moved by the observer, but the light from A prime has not yet reached him. So that's what they're saying, okay? That's why he thinks that, because when they strike for her purposes at the same time, because he's moving toward it, okay, he thinks he sees that one first and that one later because he's moving away from this one and toward that one, okay? So that's why simultaneity would not be true, because she sees them as simultaneous, he does not, okay? The two observers must find that the light travels at the same speed. That's a given. Observer O concludes that the lightning struck the front of the boxcar before it struck the back. That's O prime, the guy inside. That they were not simultaneous events because, now again, assume this is a really long boxcar going at a high rate of speed, and even though they hit at the same time, he's going faster and will sense that light before he senses this one. But on the ground, they were simultaneous. So yeah, I think if you consider that's a very long boxcar moving at a really high rate of speed, I think you can see that. Okay? So that shows the simultaneity from the two reference frames. Even though they're both inertial reference frames, they wouldn't be. Okay? So two events that are simultaneous in one reference frame are in general not simultaneous in a second reference frame, moving relative to the first. That is, simultaneity is not an absolute concept, but rather one that depends on the state of motion of the observer. In the thought experiment, both observers are correct because there's no preferred inertial reference frame. Neither one of them is better than the other, so you can't say this one's right and that one's wrong. They're both correct based on what they sense. Okay? So, interesting. I think what I had to do was picture this as a really long car moving extraordinarily fast. And if he's moving that fast, then he will sense that first light, the front lightning strike, before he will the second, because it has to catch up. She won't, however. She was on the ground and they hit at the same time for her. Okay. The second of these consequences, not in the same order they gave them originally, but it was time dilation. Okay? A vehicle is moving to the right with speed v. Okay, got it? A mirror is fixed to the ceiling of the vehicle. There's a mirror up there. Okay? Observer O prime at rest in this system holds a laser, so there she must be O prime. So they have O prime listed down here. That's kind of weird. Observer O prime at rest in that system holds a laser D below the mirror. Looks like it's A there. Okay. Rather strange. No, I'm sorry, a distance D below the mirror. So this distance here is the D. Okay. The laser emits a pulse of light directed at the mirror, that's event 1, and the pulse arrives back after being reflected, that's event 2. So the laser light, now, here's my next assumption. This is how I can understand this. I don't think you need to do it. But let's say this is a really tall boxcar, okay? Really, really, really tall boxcar. And that mirror is a long way from. So the laser emits a pulse of light directed at the mirror, event 1. It arrives back after being reflected, event 2. So the observer O prime, this is her, okay, sees the light pulse move up and then down after a total distance of 2d. D up and D down. Okay? That's the setup. Now, here's the moving observer, that's O prime. Observer O prime carries a clock. She uses it to measure the time between the events. That's delta T of the pulses. Or, proper. The P stands for proper. Delta T proper. Okay. She observes the events to occur at the same place. The delta T is the distance divided by speed. The distance is 2d, and the speed is the speed of light. So the delta T is 2d over c. All right? That's what she observes. That's what she senses. Okay? She understands that. Okay? Now, the stationary observer, O, okay, standing on the ground, that boxcar is moving by really rapidly, a large V. He observes the mirror, O prime, move with the speed of V because it's attached to the boxcar. The time the light from the laser reaches the mirror, by the time it does, the mirror has moved to the right, okay? Because this boxcar is moving really fast. So she fires it up there, and for her it goes straight up and comes straight back down. But for him, he sees her fire it, but because it's going with the boxcar, it hits the mirror there, she's still here, it hits, comes back down, that's when she receives it there. But see, relative to him, she's moving, so therefore the laser beam has to move. Okay? Now, the light must travel farther with respect to him than it did her. She just saw it go up and down, and that's what she measured, but he saw it go over here and come down here, a much longer distance here and there. Okay? But guess what? The speed of light is the same for both of them. So therefore, if the distance is greater, the speed's the same, then the only thing that can be different is the time. So that's why we call it time dilation. The light must travel farther with respect to O than with respect to O prime. And observer O sees the light pulse move on a diagonal path and measures a distance of travel greater than the 2D. Significantly greater, especially if this is a really fast train and a really high ceiling there, that would be somewhat larger. Okay? Now the distance between here and here is d delta t. D is velocity of the train, delta t is that time interval. Both observers must measure the speed of light to be c, that's the key, and the light travels farther for the ground-based observer, and the time interval delta t for the ground-based observer must be longer than the time interval O prime, which is your, what did they call that, proper time? That's what she was measuring. So he has to have a longer time interval than she would have, because the distance traveled is longer, but in the same speed of light. Okay? So the time is dilated for him, meaning grown bigger. For her, it's the reverse of that. Now, here's the okay. Here's the difference here. She sees the light go up and come back, so that's the distance d. He sees the light go up here, because it's here when, relative to him, when she's shown the light, that's when it hit the mirror, and that's when it comes back down. So, the distance traveled for her is 2d. The distance traveled for him, okay, where is the 2 coming from? Okay. Delta t for him is from here to here, then this would be delta t over 2. So the velocity times delta t over 2 would be this leg. The d would be that leg, that's the distance he travels. This velocity times time would be distance. And c delta t over 2 is the hypotenuse. Okay. All right. I think they've done a really lousy job of that proper. Let me go back and see that again. Observer A, Observer O prime carries a clock and uses to measure the time interval delta t proper. That's what she on the train is measuring. And it'll say, we'll see in a moment. Okay, I guess we will. I agree with these things. I just that delta t proper is her clock. Basically, that's all it's saying so far. His clock must be just the delta t. Okay? And we see here that this denominator here, 1 minus v squared over c squared, this is a fraction, a fairly small fraction. 1 minus that, though, is something less than 1. So if you're dividing by something less than 1, you're multiplying by something greater than 1. So the gamma there must be greater than 1. And they say this happens to be 1 over this thing. Okay. Observer M measures a longer time than observer O. That's his measurement, that's her measurement. So sure enough, it would be longer. And this, for her, the woman to measure up and down here, that's her TP. While she's doing that, this one's measuring here, then here. That's the up part, that's the down part. This is D, which is half of 2D. So that's why these are all halves. But the triangle makes it easier to see. And this thing squared is equal to this thing squared and that thing squared. Okay. All right. So the summary of time dilation. At time delta t between two events measured by an observer moving with respect to a clock is longer than the time interval delta t between the same two events measured by an observer at rest with respect to the clock. The clock moving past an observer at a speed v runs more slowly than the identical clock did at rest with the observer, with respect to the observer, by a factor of gamma to the minus 1. That effect is known as time dilation. Okay? All right. I think I'll buy that. Now, identifying the proper time, whatever that was. The time interval delta t proper is called the proper time. Proper time is the time interval between events as measured by an observer who sees the events occur at the same position. You must be able to correctly identify the observer who measures the proper time interval. If you miss that, I think you miss the whole gist of the problem. Okay? So that observer who sees the events occur at the same position, that's going to be the one that's the proper time. Okay? Nothing really proper or improper about it. His time's as good as hers, but that's what we're going to call the proper time. The view of O prime, that O is really the one moving with the speed of V. Okay, this is an alternative view. Okay, let me find where this is. I don't see this alternative view. Not sure. I see what this is. I bet you it's in there somewhere. The view of O prime, the one that's in the box bar moving, that O is really the one moving. That's what she thinks as she sees him fly by in opposite direction with the speed V to the left, and O prime's clock is running more slowly, is just as valid as O's view that O prime was moving. The principle of relativity requires that the views of the two observers in uniform relative motion must be equally valid and capable of being checked experimentally. Okay? If then you assume that the one moving was the valid one, I still guess you call the other one proper because of the way we defined it. That's interesting, okay? Now, generalization of time dilation. Okay? All physical processes slow down relative to the clock when those processes occur in a frame moving with respect to the clock. All physical processes slow down relative to the clock, a clock, when those processes occur in a frame moving with respect to the clock. These processes can be chemical and biological as well as physical. Okay? Now, I don't know if you have followed what they've done with NASA so far. I can't remember which one of them it is. One of the astronauts that's gone up many times and has been in space for long periods of time, moving at very rapid speeds, has an identical twin on Earth. And they have studied the two of them like crazy, okay? And so they're looking at some of the chemical and biological processes that are going on within them. And if I'm not mistaken, they have shown some of this time dilation to be valid. Like it says, they're verified by various experiments. One of which I think is that twin. Now, before we get into exactly what that is, I think there is one more quick quiz, another quick quiz anyway. Suppose you're an astronaut being paid according to the time you spend traveling in space. You take a long voyage traveling at near the speed of light. Upon return to Earth, you're asked how you'd like to be paid, according to the time elapsed on a clock on Earth or according to your ship's clock. To maximize your paycheck, which one should you choose? The Earth clock, the ship's clock, or either clock is good because it doesn't make a difference. Okay? Now, according to what we just said, the proper time was the one on the ship's clock. So the Earth clock is going to show a longer time because the distance traveled is longer, but the speed of light's the same. So I think he'd better go by the Earth time. That would be A. Y'all agree? Okay. Let's see how easily I can talk you into stuff. Okay. 26, 2, sure enough, is A. All right. Now, well, should have done, well, I don't know, they have these in different order. Yes? Yeah, we got the lab from the last chapter. Is it time? It's getting close. 5 minutes. Yeah. Okay. It's going to take me a little while to set up, but I think we'll be able to get it done fairly quickly, especially since we only got 4 people here. Okay. This is in your text on the bottom of page 845. In 1976, experiments with muons, I don't know if you all are familiar with what muons are. They're elementary particles, and because they're particles, they don't travel at the speed of light, but they're very small particles, so they may get very close. Were conducted at European Council for Nuclear Research, that's CERN, that in France they would say Council European Research Nuclear. Okay, that's why the letters are backwards. In Geneva, the muons were injected into a large storage ring, reaching speeds of about 0.9994 times the speed of light. That's awfully close. Awfully close. Electrons produced by the decaying muons were detected by counters around the ring, enabling scientists to measure the decay rate and hence the lifetime of the muons. The lifetime of the muons was measured to be about 30 times as long as that of the stationary muons, to within 2 parts in 1,000, in agreement with the prediction of relativity. Okay? So let's see this again. All right. Without taking into account relativity, very few muons created in the upper atmosphere would be expected to reach Earth before decay. Okay? So a muon is created, and 6.6 times 10 to the second, that would be 660 meters later, the muon decays. Experimentally, however, far larger numbers were expected to reach, far larger numbers than expected actually did reach the Earth's surface. Okay? Muon was created up there and decayed 4.8 times 10 to the third micron meters later. It decayed on the surface of the Earth. Muons are unstable particles that have the same charge as an electron, a -1 charge, but a mass that's 207 times more than that of an electron. An electron has a fixed mass. So these are more massive than an electron, but the same charge. Muons have a half-life of delta T being 2.2 microseconds. They're measured in a reference frame at rest with respect to them. There is a citation there, we just don't see it. Relative to an observer on Earth, the muon should have a lifetime of gamma, but relative to an observer on Earth, muon should have a lifetime of gamma delta T E. That's gamma times this, 2.2 microseconds. Another reference there. A CERN experiment measured lifetimes in agreement with predictions of relativity. So that would be that one rather than this one. Okay? So they were much, much, much smaller. Okay? What surprises me is something with that much mass can travel 0.9994 or something like that times the speed of light. That is incredibly fast for something with some mass whatsoever. Okay. Now, the twin paradox. I think this may be a good place to stop. Okay? We're not going to be able to get very far, and we're right close to the 7 o'clock start time. So we will begin next time with the twin paradox. This is going well. I have a lab today, so we didn't have much time. I got started late, and I've had to repeat some things. So we've still got to finish 26.4. We got 26.5.6. 26.5 is very short. 26.6 to 7, that's very short. 26.7 is a bit longer. Then 26.8 is general relativity. You know, we might be able to finish this. I think we will finish this next time. And and probably go back and start on, what was the other chapter? Chapter 20, I believe it was.
So this
So-
will be our last lab.
No. We're going to do the lab right now, but then if we finish 20, we may have a lab again.
But that probably won't be till like 20, right?
Yeah, oh yeah, it won't, yeah. But this will be. Now, I don't have enough labs copied for everybody if all 8 people were here, but I have enough for 4. So we will go down and proceed with this. What I'm going to do is stop this. It's running. All right, doing the lab. This is actually lab 7. I think it says 8. Y'all didn't have a 7. The last lab you did was 6, I believe, wasn't it? Go, okay. First, I gave each team a plane mirror, and they were to hold it a comfortable distance from your face, hold a ruler next to your face, zero the ruler at the top of the mirror, read the length of the mirror that you saw in the mirror in centimeters, and record it there, and all of you recorded that. Measure the length of the mirror and record it, and then what is the ratio between the two. And then we did a curved mirror, placing it on and you'll just have to get the lab. Sorry that I forgot to turn on the recorder. You should have been here.